The goal of this video is to be able to create a simple sampling distribution. The word simple is used here because we're going to use one that the population is very small, much smaller than would realistically be done for a full statistics problem, but it gives us all of the details and pieces. For our scenario, there are 4 families in my small group from church. The families have 1, 2, 3, and 6 children respectively. My family's that one with 3 children. We will use the number of children of our families in my small group as our complete population. So you see here, very small population to keep things simple. Our goal: if 2 families are randomly selected with replacement from this population, we want to identify the sampling distribution of the sample mean by creating a table representing the probability distribution of the sample mean. And then the question: does the mean of the sampling distribution target the mean of the population? So that task seems overwhelming because the language is so complex. Let's take a look at what we need to do. We want to create the sampling distribution. We have our population, 1, 2, 3, or 6 children. Our sample size from the previous slide we were told was 2. That literally means we're going to pool 2 families from our population. We're going to pool them with replacement, so we could get the exact same family twice. So if I pool, and I'm just going to do this very systematically, not randomly at all, but I want to list for a distribution all the possible outcomes. So I could pool the family that had 1 child, and then the second time I put that family back, because we're doing with replacement, I could pull them again. Or I could pull the family with 1 child and then with 2 children. Or 1 child and then with 3 children. 1 child and then with 6 children. Similarly, I could start with the family with 2 children and then pull the one that had only 1. Or I could pull the family that has 2 children twice. And I think you start to see the pattern that I'm using here to list all of my different samples that would be part of this distribution. And I'll repeat, starting with the family with 3 children. And I'll end up starting with the family that had 6 children and all the different possibilities as far as the different samples, size 2, that I could make. Now, the next column I need to calculate the sample mean. This will be easy because my samples are so small. So I'm going to add these 2 numbers together, divide by 2. So 1 plus 1 is 2. 2 divided by 2, because there's 2 in there, is going to be 1. So it's okay to have decimals. This would be 3 divided by 2, or 1.5. 4 divided by 2 is 2. 7 divided by 2 is 3.5. 2, 3, so 3 divided by 2 is 1.5 again. 4 divided by 2 is 2. 5 divided by 2 is 2.5. 8 divided by 2 is 4. 4 divided by 2 is 2. 5 divided by 2 is 2.5. 6 divided by 2 is 3. 9 divided by 2 is 4.5. 7 divided by 2 is 3.5. 8 divided by 2 is 4. 9 divided by 2 is 4.5. And 12 divided by 2 is 6. So this is all my possible samples and the mean of every single one of those samples. Now, that's a lot of information. We want to condense a little bit because as I look through these means, I see that there are some repeats. So I'm going to take the information from here and convert it over to a slightly smaller chart. The first column now is my sample mean. So the different options, I have to list all of them, are 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 6. Those are all the different means for a sample of size 2 that has been pooled from our original population. We're now ready to calculate the probability of each mean. In order to do that, we're going to look at our
table and see how often it occurred. In our table, we took 16 samples and calculated 16 sample means. Out of all of them, the sample mean of 1 only shows up one time, so the probability of getting a 1 is just 1 out of 16. If I would prefer that as a decimal, I can put that on my calculator as well, and I get 0.0625. Next, I need to find how many times 1.5 occurs as the mean. So we already used this one. There's a 1.5. Here's a 1.5. So 2 out of the 16 times. As a decimal, that's 0.125. Next, we have 2, and I see that 1, 2, 3 different times. So 3 out of 16. Which is the decimal 0.1875. Next is the 2.5, and I see that 1, 2 times. Next is 3, and that's only there once. 3.5 is there 1, 2 times. 4 is on the list once, twice. 4.5 is there twice. And 6 is just there once. Now keeping these in fraction form is helpful because I can double check. And so I have 1, 3, 6, 8, 9, 10, 11, 13, 15, 16 total. And so that meets my characteristic of a probability distribution because that adds up to 16 out of 16, which is 1, and that is a requirement. The next step is actually to find the mean of this probability distribution. So I have the column here prompting us exactly what to do. We're going to take the m, that's our data, multiply it by the probability of that outcome, and we created a list before when we did this, and we're going to do that again. So this is where having the decimals is nice, and we have these decimals repeat. You can use your calculator to help you. So for this first one, 1 times this decimal is 0.0625. Next, we'll take 1.5 times 0.125. So that's the m value times the probability of m. And put that on our calculator, 0.1875. You can pause the video as you do all of these and then turn it back on and double check your work with mine. Now that we've completed all of the mean times the probability of that mean, we want to add up those values because our formula for the mean of a probability distribution is the sum of all of these. So again, I'm going to go to my calculator. I'm going to type in this answer plus this one, so forth on down through there. And when I do that, I come up with exactly 3. Now, the question that we were actually asked is, does the mean of the sampling distribution target the mean of the population? We just found the mean of the sampling distribution, and we found that that was 3. So now we have to find the mean of the population and see if they match. So our population is up here. If we're going to take the mean of it, we'll take 1 plus 2 plus 3 plus 6. Divide that by 4 because there are 4 pieces of data, so this would be 9, 10, 11, 12 over 4, which is indeed 3. And so yes, the mean of this sampling distribution, which is 3, does target the mean of the actual population. And we'll learn in our notes a bit later on that the mean is an unbiased estimator, meaning that this always happens, that when we take the mean of a sampling distribution, it is estimating, in our case exactly, but estimating the mean of the population.